Welcome to the Electrical and Electronic Engineering Lecture Series. The anchor person is Professor Michael Sindinechi. Our topic today is Module 044, Zener Diodes. We'll be talking about the principles, characteristics, and applications of Zener Diodes. Please follow me in the engineering lecture series by subscribing to my YouTube channel. My YouTube channel is https://youtube.com/@ndinechimichael.c. Please like, share, and drop your comments in the comment section. This lecture, Zener Diodes, is an offshoot of an earlier lecture I had on semiconductor electronics, and you can listen to that lecture using the link given. And also, I had done an earlier lecture on transistor electronics. You can as well listen to that lecture using the link given. More so, I would like you to visit Ebony Educational Consult website at www.ebonyeducationalconsult.com for more free engineering lectures. Now, as we start our lectures on Zener Diodes, I would like to go through quickly on what I call semiconductor electronics, because it is important for you as an engineering student, more especially electronic engineering student, to know the build-up to Zener Diodes. And the starting point is to know about semiconductors. We know we have two types of semiconductors, the intrinsic and the extrinsic semiconductors. Let us start by looking at the intrinsic semiconductors. Materials in their pure state can be classified as conductors or insulators. However, some materials, when in their pure state, behave as insulators, but when doped with other materials, behave as conductors. These type of materials are called intrinsic semiconductors, and they have conductivity intermediate between conductors and insulators. We know that conductors have resistivity of the order of 10 raised to power minus 6 ohm cm. Here, the valency electron is so loosely bound that it can readily escape and is then free to move throughout the crystal lattice. This allows the electric current to be easily produced within the application of an electric field of any magnitude. On the other hand, insulators have resistivity of the order of 10 raised to power 14 ohm cm. Therefore, there are as many valency electrons as there are in the energy levels in the valency band. Consequently, no valency electron in the full valency band can absorb the energy given by an electric field unless another electron takes a lower place. Then this cancels the current due to the first electron. While there is an upper empty conduction band, the relatively large gap of a few electron volts is such that moderate values of electric field strength do not provide enough energy to move electrons across the gap. If you illustrate it in your basic chemistry class, you see that, materials, we have their, valency band and energy level that enables, when energized, allows electrons to move. Well, this is the chemistry of the materials, which is, exploited to produce this diode we are going to look at. Now, on the other hand, insulators do not conduct, at least not until the applied voltage is sufficiently large to force the electrons across the energy gap when the material then breaks down. What we are saying here is that even though you see some materials, say, they are insulators, you use them to cover, conductors. Yeah. If you apply sufficient energy or heat, then at certain point, that insulators will break down and become conductors. It is important for us to note this because the Zener diodes make use of this principle. An increase in temperature, if great enough, will cause sufficient thermal agitation for some electrons to cross the gap to the upper empty band. This process is known as thermal excitation, and in general, the conductivity of insulators tends to increase with temperature. If you have a conductor and you apply temperature at certain point, that insulator will intend to conduct. Now, most of the common materials we have, like germanium and silicon, when they are pure, they behave as insulators, and they are said to be an intrinsic semiconductor. Remember, when they are pure, they behave as insulators. But something happens when they are no longer pure, that is, in their natural state. As a result of thermal excitation, electrons are raised to the conduction band of such materials, and they contribute to electrical conduction. At any given temperature, materials with small energy gaps conduct more readily. Thus, the conductivity of germanium at room temperature is very much greater than that of silicon. The movement of electrons from the valency band to the conduction band causes the valency band to be no longer completely filled. Some valency electrons can gain energy from an applied electric field to occupy levels left vacant by those electrons that have moved to the conduction band. This in effect is the movement of positive holes in the valency band. Conduction in the material is thus in terms of negative and positive charge carriers, which we call electrons and holes in equal numbers. Let me throw more light here. If you see where charges are represented in your physics, in your chemistry, you see that you have small circle with plus sign inside, and you also have small circle with minus sign inside. The one you have with plus sign inside is called the positive charge, and the one with the negative sign is called the negative charge. Now, we are saying that when you have that negative charge, call it electrons. When you have the positive charge, you call it holes. Meaning that for conduction to take place, this negative charge must move to take over the positive charge, while that positive charge will, move on. As this is happening, it constitutes the flow of current in that. Now, like we have said, the semiconductors are two types, intrinsic and extrinsic semiconductors. Now, we've talked about intrinsic semiconductors, which is when they are in their pure state, behaving like insulators. But when you energize them with force, they tend to conduct. Now, when the intrinsic semiconductor tends to conduct, they become conductors, but their conduction or their conductivity is very low. Now, you want to do something to make that conductivity give you what you want. Then you go on to dope it with some materials. When you do that, you have what is known as extrinsic semiconductor. Now, this extrinsic semiconductor is very, very, very useful in electronics or in electronic engineering. And the first thing it gives is this diode we are talking about. So the relative low conductivity of an intrinsic semiconductor may be increased considerably by the introduction of impurities. When impurity is introduced to a semiconductor material, the resulting semiconductor is called an extrinsic semiconductor. Here, conduction occurs, and at normal operating temperature, this is large enough compared with that of the intrinsic conduction component. So, see, just small introduction of an impurity material. As we go on, we will see what constitutes these impurity materials to this semiconductor material. The resulting semiconductor out of that introduction of impurity is called extrinsic semiconductor. And we say that at this point, conduction occurs and, at normal temperature without being energized separately. That is what we mean by normal operating temperature. And the conduction that takes place is very large compared to what it is when that material is in its natural state. Now, the first thing that occurs when you introduce impurity could be an N-type semiconductor or P-type semiconductor. By the time we say N-type, we are talking of negative type semiconductor. In other words, we are talking of when you have the small circle with a minus inside the small circle. Call it N-type semiconductor or negative type semiconductor. Now, so if a pentavalent impurity element such as arsenic or antimony, arsenic material, antimony is also a material. Your basic chemistry, you must have seen all these elements stated, germanium, silicon, arsenic, antimony, and all those materials. So we say that if a pentavalent impurity element such as arsenic or antimony is introduced into, for instance, a germanium crystal, then only 4 of the 5 valency electrons in each atom is used in forming covalent bonds with the nearby germanium bond. Now, germanium, which we said is a semiconductor, that is, behaves as insulator under, a natural state. We're not saying if germanium has 4 outer shell electrons, if you remember your chemistry very well, then if you dope it with antimony, which is a material with 5 outer valency electrons, the 4 in the germanium and the first 4 in the antimony will form covalent bond, then 1 will remain, and that one will be dangling, looking for what to form covalent bond with. So that one that is dangling is now being made use of. The 5th one, or the 5th electron, at even relatively low temperatures, requires sufficient energy for it to break away and be raised into the conduction band, where it can move freely and increase the conductivity. Atoms of impurity elements with 5 valency electrons are referred to as donors because they donate electrons to the crystal. Let us get it very well. So these materials with 4 outer valency electrons are called semiconductors. They act as insulators when in their natural state. Now, when you dope them with another material, which you call the impurity material, we say, for example, doping it with antimony. Now, antimony has 5 outer valence. Then, when they form the covalent bond, they 4 from germanium and the 4 from antimony will form a bond. One that is looking for another to form a bond will be free, waiting for anything to happen. So with the slightest energy push, which could be as a result of temperature change, we force that extra one to quickly move and to the next atom. So say these atoms of impurity elements, which is dangling, is called donors because any material around it, it will be donated to that material. So they are called donors because they donate electrons to the crystal. Now, remember, electrons, when we talk of electrons, we see that small circle with minus inside, we call it electrons. So that minus is what gives this type of semiconductors N, because it's like negative. So the semiconductor is then said to be N-type or negative type because electrons carry negative sign. In such materials, the electrons are the majority carriers as opposed to the thermally liberated holes, which are minority carriers. It is very important for you to know here and always commit it to memory that in the N-type semiconductor, the electrons, which is the circle with minus inside, which made the name N-type, that these electrons are the majority carriers. That is, they are more. They are the ones that are liberated to move to another, the next atom and to the next atom, and that is what constitutes electric flow in that material. So say, note also that in N-type material, the impurity atoms become positive ions which are not free to move. Thus, donor atoms provide fixed positively charged ions and an equal number of electrons which move about in the crystal. The material as a whole is electrically neutral or uncharged. Then the other one, which is the p-type semiconductor, we also record that the intrinsic semiconductor atoms may be displayed by atoms of a trivalent element, such as boron or gallium. Trivalent element means those elements with 3 outer state electrons. In this case, there is an incomplete valency band. The missing electron constitutes a hole which may be neutralized by an electron moving into it from a nearby bond. Recall here, the outer valence electron of the material you are using to dope or you are introducing as impurity material has 3 valence, and you are adding into, let's say, germanium that has 4. So only 3 of the germanium and that of the boron will form covalent bond. Then 1 of that outer valency electron will be looking for what to combine with. So say in the absence of external forces, the whole moves at random from one covalent bond to another and acts as a positive charge carrier. Atoms of these materials are referred to as acceptors because they accept electrons from any adjacent germanium or silicon atoms. The semiconductor is then said to be the p-type because it has the positive sign. So here, the holes, which is that small circle with plus sign, are the majority carriers as their number is very large compared with the thermally liberated electrons, which are the minority carriers. Now, when you have these two materials come together, the one that is the N-type that has electrons in excess and the one that has holes in excess are brought together by alloy. See that that extra hole in one and the extra electron in the other one will take up the vacancy or the spaces created. When this happens, you call the point where this p-type and the n-type material come together as the p and n junction. So say this PN junction refers to a boundary between the two types of semiconductors in such a way that the material is in effect a single crystal with lattice structure matched throughout the junction area. Such an interface may be produced by alloying. In your basic chemistry, you have treated alloys and methods of, bringing materials together in by form of alloying. You have, bonding, you have alloying. So, say this process of PN junction coming together is produced by alloying. The formation of PN junction causes some holes from the p-type material and some electrons from the n-type material to diffuse towards each other and combine. This process occurs momentarily in the intermediate area of the junction between the p and the type material, which is known as the barrier region. The fixed positive donor ions in the n-type material and the fixed negative acceptor ions in the p-type material are left uncompensated. The difference of potential and hence electric field established across the junction is such as to prevent further movement of both holes and electrons at the junction, thus giving rise to a depletion of discharge carriers at the junction. The region where this takes place effect is referred to as the depletion region. The concept of this PN junction is very necessary in electronic engineering because it forms the basis for all electronic component design. Now, let me try to draw a quick analogy on what we have done. Assuming we have two teams. One team is, two teams. One team is wearing red, the other team is wearing blue. Now, the two teams come together to a point, and the first line in team blue is 10, the first line in team red is 10, and they are to shake hands. You see, the first 10 people in front will shake hand, then the people behind the first line in the red side will not have space to shake hand with the people behind the first 10 in the blue side. So at that point where they meet, it becomes where is known as this barrier region, because at that point, the people behind in the blue side are prevented from shaking hands with the people behind in the red side. So until these first line people move across the boundary, the interface where they meet, they will be able to shake hands with the people behind the other side, and these people will be able to shake hands behind the other side. So this movement of applying a force that make the first line people to cross to this line or to cross to this line is what constitutes the flow. That flow, in the sense of electronics, is the flow of current. So as they move, these people will be able to shake more hands inside or deep on the side of the red, and the blue people will also, and the red people will also be able to do same on the other side. So as they do that, they, they constitute the flow of electric current. But at the point where they meet the first time, if there is no force to cross them, it becomes a barrier. And this place where there is this barrier is where we call the depletion region, because at that point, the first line from this side and this side has come together and joined together as a bond. When they bond, they will not allow another to move across until there is a force to, do that. So now, at this point where they meet, we now call this point, and what happens there? A diode. We say a PN junction is also referred to as a diode. And the diode, semiconductor diode, is a junction between a P-type and an N-type semiconductor, which is known as PN junction. It allows current to flow in one direction, but restrains the flow in the other direction, except for a small leakage current. The circuit symbol for a diode is as shown, is, simple as that. Current will flow in the direction of the arrow. Semiconductor diodes are used in a variety of applications such as clippers, comparators, rectifiers, and voltage doublers. These are common circuits you see in electronics. So this diode has, general characteristics, and the general form of the characteristics is referred to as IV, that is current voltage characteristics, as we can see very soon. The current flow in the forward direction is very large compared with that in the reverse direction. The reverse current through the diode varies greatly with temperature and with the semiconductor materials used. If the reverse voltage is sufficiently large, the reverse current increases sharply and the reverse voltage breakdown occurs. In the reverse bias condition, the reverse saturation current, otherwise known as the leakage current, is of the order of several nanoamp to several micro. Leakage current is very temperature dependent and is found at the reverse saturation current approximately doubles for every 10 degrees centigrade rise in temperature. Now, what we are looking at is the plot of the IV current voltage characteristics of a typical silicon diode, where when you say a diode made from the doping of silicon material. So you see, to the right is the forward bias. So when the current voltage is, increased in the forward direction, as we said in the diagram of the diode, current flows in the direction of the arrow. So when current flows in the direction of the arrow, at certain point, when the voltage gets to just about a little above 0.6 volts, the current rises sharply. You can see how the current rises sharply after 0.06. So if you apply current in the negative direction, that is in the reverse direction, you will see that at certain point, the current flows again, but that current flowing at that point, doesn't have high values. You can see it is in the order of microamp, while in the reverse direction, the current rises in tens of milliamps, that is up. So now the Zener diode, as you can see, we make use of this reverse operation to work. Let's go on and see it. So at the reverse breakdown voltage, or what is known as the peak inverse voltage, the diode will break down, and unless the current is limited by a resistor, the device will be damaged. Diodes are not used on this part of the characteristics, except in the case of Zener diodes. So, a Zener diode is a special type of semiconductor diode designed to allow current to flow not only in the forward direction like a regular diode, but also in the reverse direction when the applied voltage exceeds a specified value known as the breakdown voltage. It is widely used for voltage regulation, overvoltage protection, and reference voltage generation. So the symbol of the Zener diode is shown. You see that for it's the same thing as the simple diode, but the cross after the arrow is bent forward one side, backwards the other side. So Zener diodes operate in two modes. Have what we call the forward bias mode, and we say that in the forward bias mode, it behaves like the regular diode. In that forward bias, the current flows when the forward voltage exceeds approximately 0.7 volts for silicon, as we have seen in that figure 2. So in the reverse bias mode, only small leakage current flows. As we can see in that plot that, it is in order of micro amps, very small. So when the reverse voltage reaches its breakdown voltage, known as the VZ, it conducts heavily. The voltage across the diode remains nearly constant at VZ despite changes in current. Now, this breakdown mechanism occurs in two ways. One is called the Zener breakdown. I would say at Zener breakdown, the breakdown occurs due to strong electric field pulling electrons from covalent bonds, and is prominent in low voltage Zener diodes. We also have what is known as the avalanche breakdown, which occurs due to impact ionization, where carriers gain enough energy to free additional carriers, and is prominent when you make use of high voltage. So the applications of these Zener diodes include voltage regulation. It helps to maintain constant output voltage in power supplies, because we have seen that in that plot, even if the temperature is increasing, if the voltage is increasing, the current remains almost constant. If you look at the plot, you see that at certain voltage point, the current rises sharply. So it's also used for protection, over voltage protection. So you use it to protect your sensitive circuits by helping to clamp excess voltage supply to that circuit. Also, Reference voltage sources. It provides stable reference in measuring circuits. Also, you can use it for waveform clipping and shaping. So it limits signal amplitude in wave shaping circuits. Advantages include simple and inexpensive, provides stable voltage over wide current ranges. That is, if you it doesn't matter the current, you want to maintain your voltage at a point, you make use of Zener diode. It also has some limitations that it is not stable for high current regulation. Voltage tolerance depends on manufacturing precision, and it has power dissipation limits. Conclusion: the Zener diode is an essential component for voltage stabilization and protection in modern electronics. If you're designing your power supply circuit and you want a stable voltage output, you will likely use Zener diodes to obtain that. So understanding its breakdown mechanism and proper biasing is crucial for designing reliable power supplies and protective circuits. When you will be doing your final year projects, you are required to do some. So that is. Watch out for our next lecture, which is on Schottky diodes. Thank you for listening.